All right, hello everyone, and welcome to our 9 a.m. press briefing, The Sun to Interstellar Space, 6 new missions piecing together the space weather puzzle, sponsored by NASA. In just a moment, I'm going to introduce Abby and her team to introduce all the scientists to you, but some quick notes. We're going to do about 20 minutes of presentations, then we'll open to Q&A. You can just raise your hand if you're in the room, and Abby's going to call upon you to have you in. And if you're online, you can drop your question into the Q&A box at any time. We'll get to you in the order where they're received. Please identify your name and which organization you are writing for. And with that, I'd like to turn it over to Abby and the NASA team.
All right, thank you, Liza. Hi, I'm Abby Interante, and I work in communications for heliophysics at NASA headquarters, and I'm so excited that you all joined us today. We have had a really big year, and the folks here are going to tell you all about it. So to my right, we have Sal Masseri, who is our Acting Associate Director for Flight for heliophysics at NASA headquarters. We have Dave McComas, who is from Princeton and is the principal investigator for IMAP. We have Craig DeForest from Southwest Research Institute, and he is the PI for Punch. We have Rob Lillis from UC Berkeley, and he's the PI for ESCAPADE. And then we have Laura Waldrop, who is from University of Illinois Urbana-Champaign, and she is the PI of the Carruthers Geocorona Observatory. So I'm going to go ahead and pass it off to get started.
Thanks, Abby. Hi, everyone. I'm here to talk about this milestone year for heliophysics. This has been an amazing year for us, from missions, sounding rockets.
Yep, there you go.
And next one. Thank you. So it's been a milestone year for us, from mission sounding rocket CubeSat launches to seeing amazing auroras across the world, the word heliophysics making it into the dictionary, and our active missions returning some incredible science, like Parker Solar Probe's findings from inside the sun's atmosphere. So NASA's fleet of spacecraft, some of which you see here, they study space weather from its start at the sun to its furthest reaches on the very edge of the sun's influence, the heliosphere, and key locations in between. As humanity expands and explores beyond Earth, our recently launched missions will add new pieces to the space weather puzzle. And that fills the space between Parker Solar Probe at the sun to voyagers beyond the heliopause. These missions, many of which are made of lower cost, small satellites, collaborate with commercial partners, use rideshare opportunities to achieve their goals in a faster, more efficient way. This has been made possible because and it's made vital research possible, and even we're going to go to Mars at a totally different cost. Astronauts traveling to and exploring on the Moon and Mars will operate outside of the Earth's protected magnetosphere, exposed to the harshest elements of deep space, including coronal mass ejections and X-class solar flares. And in addition to the constant stream of solar wind that's coming from the sun, and this research that we're doing in heliophysics will create a resilient society that will thrive while living with our closest star. Next chart, please. So these are the missions that we launched in 2025, from January all the way to last month with ESCAPADE. And we chose these missions to help safeguard humanity's home in space and revolutionize exploration of the only known habitable star, which is our sun, and everything that it influences. We selected tracers and punch together, both as a new way of doing higher risk class missions as small explorers. EZIE, as a mission of opportunity, showed that we can really make a small, high-risk new technology and fly them. It was also, on top of that, a PI-procured launch, and that was totally new for us. IMAP was our first true PI-led strategic mission. That's the future of strategic missions that was done on cost, schedule, and below a level of a flagship mission cost. Carruthers made use of the additional launch capability on IMAP and worked in a high-risk, do-no-harm way. And then ESCAPADE. Well, they'll tell you more, but there is nothing regular about ESCAPADE. Next job. So our PIs here will tell you more about their missions. The two I want to touch on before I give the floor to Craig are tracers and EZIE. EZIE launched in March as a small sat, a mission with big science return. It's a set of 3 small satellites, 3 CubeSats that are designed to study the auroral electrojets, which are electrical currents flowing about 60 to 90 miles above the poles and link beautiful aurora to Earth's magnetosphere and respond to solar activity and other drivers. It is a mission that will provide the first systematic measurement of these electrojets. And we've never been able to make these measurements before. This mission helps scientists understand the sun and the Earth as an interconnected system, as NASA is yet to understand the basic configuration of the electrical currents, which are central to the interactions between the Earth and the surrounding space. All spacecraft are fully operational, and the instruments are performing beyond expectations and returning amazing new data. And you see some of that data, the EZIE first slide on the left. And this data is actually now available to the public, and the team just published it for the community to use. On the right, we have tracers. We launched tracers in July from Vandenberg. It's a twin spacecraft mission that will help us understand magnetic reconnection and its effects in Earth's atmosphere. Just last week, we shared on our NASA blog that the spacecraft have begun preliminary tandem science measurements after working through some issues during commissioning with one of the spacecraft. And we're so excited to see what's coming next and the data that's going to come from this mission. And the issues and challenges we saw on tracers actually helped us to further enable future low-cost missions with commercial partnerships. It's amazing to see what this team is doing right now. They have created a path to work to achieve their original science by changing the concept of operations and showing an incredible dedication to the work. And this year, of all launches, it's been a fruition of experiments that started less than 10 years ago to see what we can do with accepting more risk to achieve our missions at a lower cost. And with the success this year, we've proved that this risk posture is very successful. And in fact, we may be able to push further into this space. We're excited for this phase in heliophysics research, and our fleet across the solar system, they're all studying space weather and preparing us for exploration on Mars and beyond. Greg?
Thank you. So I'm Greg DeForest. I'm PI of the Punch mission. Can we have the next slide, please? There we go. That's my title. And Punch is a wide field imaging system. I'm going to stand up. This is going to point at the screen a little bit. We have one instrument spread across 4 spacecraft. And we're trying to understand how the sun's corona becomes the solar wind. So we're bathed in the outer atmosphere of a star, along with everything else in the solar system. We don't really understand that as a connected system to the corona we can see during an eclipse. So we're trying to image that entire system as a unit to understand how the corona becomes the solar wind and the space weather that affects us. So it's 4 spacecraft spread around the Earth on the dawn dusk line. The reason for that is we have to be close to the ground to get enough data back to support the mission. But that means there's a planet in the way. So we had to make the instrument as big as the planet so we could look out in all directions. These 4 spacecraft work together around the clock all the time. They're taking an image every 4 minutes in polarized light. They're doing it right now. They go overhead every dawn and dusk. You can actually go out and see one dusk if you know where to look on the western skies. We have one narrow field imager that looks close to the sun. It's a coronagraph. You may have encountered that before. We have 3 separate wide field imagers that look out to 45 degrees away from the sun. So you're used to space telescopes from NASA. This is not a telescope. It's a wide field imager that's looking at what's happening to us now. Next slide. So this is what the spacecraft actually look like. They are small. They're about a yard long. There are 4 of them. This is them last spring, just before launch. Over on the right, they're mounted to the top of an adapter room from Falcon 9. Could we click once more? You can see 2 of the wide field imagers are here and narrow field imagers there. They launched together on March 11th and then spread out in orbit. So we achieved our constellation sometime in late July. We've been taking data ever since then every 4 minutes. So I'm going to show you some of our data next. I'm going to take a moment on this because this is an amazing sequence. This is a typical couple of weeks that you are seeing something that very few people have ever seen before. This is not a coronagraph image. This is a 90-degree swath of sky. The only proper way to display it is on a planetarium dome. This dark circle in the center here, which is the inner part of the punch data you're looking at, is also the outer boundary of where we can see with SOHO, LASCO, and with all of the other coronagraphs that have flown. So everything out here is brand new. And the pageantry of the cosmos is on full display here, right? We have 2 planets. We have Mars and Mercury. We have Venus. We've got a comet going overhead, right? The sun is drifting through the cosmos around us. This is our neighborhood. We live here. You can see the galaxy coming in. And this is what we're here to study against the backdrop of the stars. You can see the outer reaches of the corona. You can see space weather in action. And I want you to watch here as the comet sweeps around. Its tail is affected. As these CMEs cross over, you can see the comet jump in response to the wind coming off of the sun. So just in a nutshell, you can see this sort of gorgeous sense of place. To me, this feels like our version of the big blue marble picture, right? Where we're looking back at the Earth, the big blue marble from Apollo, and seeing, we live there. This is our neighborhood, right? And we can now see it in a way that we've never been able to. So that's what we're doing. And we hope to have a lot of science coming forward. Inner reaches, we're going to switch, I think, to the outer reaches. Dave, we've got some things to say.
Yeah, sorry, could you just go back to that picture very briefly? So what you're saying is, because obviously I love watching these amazing solar telescope images of the eruptions. Are you saying that the picture that we normally get is just that inside that inner black
little thing?
Yeah, and so you're now seeing the full. I mean, it's gorgeous.
That's correct. So these things are huge in the sky, right? You can't see them because they're out in the daytime.
Yeah.
But yeah.
Yeah, thanks, Craig. So I'm going to talk to you about IMAP, September 24th from Kennedy. Next, please. So IMAP is a big spacecraft. I think you called it strategic missions. So we have 10 instruments. Actually, 3 of them are dual-headed, so 13 instrument sensors. It's about 10 feet in diameter, about 4 feet tall, and weighs a ton. So it's a big spacecraft. With these 10 instruments, we've just finished turning all of them on. We're studying everything from particle acceleration in the inner heliosphere, all the way up to the interaction of the outer heliosphere, the edge of the solar system, and how it interacts with the very local interstellar medium. What you see arrayed around our spacecraft here are first results from each of those 10 instruments. I'll go very briefly through those. So we take images of the outer heliosphere with something called energetic neutral atoms. Those are single atoms that are produced 10 billion miles away by charge exchange. And when that happens, a very tiny fraction of them can come all the way back in and be observed by us near Earth or near L1. And we do that at 3 different energies that go all the way from 10 electron volts all the way up to over 100,000 electron volts. So a factor of 10,000 in energy range. The prior state of the art, which I was the PI for and the PI for also in IBEX, is a single decade. So 1,000 times broader energy range. We have overlapping energy ranges, which I'll show you a little bit about, and we're just starting to take these images at these different energies. We also have dust experiment, IDEX, which measures individual dust grains coming in from the interstellar medium. This is one of the two first dust grains that we got. This is a spectrum. I can show you in detail if you have questions later. It is a spectrum of the material in that dust grain. This is actually a planetary dust grain, but we'll be seeing both planetary and interstellar dust grains. Then also we got an instrument called GLOWS. This one was developed in Poland by our Polish colleagues and contributed by Poland. It actually measures the three-dimensional structure of the heliosphere in scattered Lyman alpha and tells us about what the structure is like so that we can put that together with the ENAs, energetic neutral atoms we're getting back from the outer boundaries. So very important measurement for us. In addition to those five, we've got 5 measurements of in situ local data around the spacecraft. They're very important for space weather as well as for science. Those are the swapping instrument, that's a low energy instrument. It actually matches up with the energies for IMAP low, so we see particles coming out from the solar wind, and then we see them coming back as energetic neutral atoms a couple of years later. From swapping, we go to CODIS, which measures the composition very well of superthermal ions, and all the way up to high energies with the HIT instrument. So those three are 3 ion instruments that match up with the ENA instruments that observe these particles coming. We see them going out, and then we see them coming back as energetic neutral atoms. We also have a magnetometer. Then we've got an electron instrument, which measures the solar wind electrons. So all 10 of those have just been turned on in the last couple of months. They're all working. We have first light data from all of them. So I call it a 10 out of 10, A+. Professor, I get to get grades. When you get a 10 out of 10, and they all work better than you expected, that's an A+. Next. So just as an example, this is the overlap from the first swath we had from the low energy instrument, IMAP low, and IMAP high, the higher energy instrument. So you can see here the data is within about a factor of 2 of each other. On the first, just the first measurements that we've made, we're still doing a little bit of tuning. We'll get this factor of 2 taken care of, but to have them that close right out of the box is really remarkable. Similarly for IMAP high, we're going up to ultra, it's all the way up to 100 keV, it's all the way down to 10 eV. For IMAP high and IMAP ultra, you can see that we get good overlap between those two. This one was turned on earlier than low, and this one actually makes measurements the highest energy, makes measurements in a different way that it sees more of the sky notes. So we've already started to fill in some of the sky with the mappings from ultra. You can see again this very good connection between the two in the spectra, and this sort of factor of 2 that we're still tracking down. Another really interesting thing is we started turning the IBEX spacecraft, which we used to turn every 5 to 7 days. We started turning it every day by 1 degree, just exactly to match the IMAP pointing every single day. And you can see here the overlay in black with IMAP high in green, and they're almost identical, which means we're going to be able to tie together the 17 years of IBEX observations with the much higher sensitivity and resolution measurements from IMAP. So we'll get the 4th dimension of time, as well as the 3 dimensions of space, sort of, again, straight out of the box. Next, please. And then just briefly, particle acceleration is really important for us for a lot of reasons. This is an example of a coronal mass ejection coming off. There's magnetic reconnection, which makes high energy particles. Shocks form in front of fast CMEs, and they get driven out, again, particle acceleration. And when those things arrive at IMAP at L1, then we basically are able to take measurements with our 5 in situ observations, electrons, ions, and magnetic field, and those are telemetry back. So we get about a 30 to 40 minute warning at Earth before the space weather arrives at Earth. And so it's very important that those data not only come down scientifically, but they also come down in real time. So we're constantly telemetry data from these 5 instruments was picked up by ground stations on Earth, sent to our science operations center, and within 5 minutes we turn that data and it's back out for the world to use for space weather, early warning, advanced warning. People even will be able to run models from this data. It's early enough that they'll be able to do complicated models and get even finer predictions than just looking at the data. So that in a nutshell is I'm happy to answer questions when we're done with this. Laura, over to you.
Great. I also like to point at the screen. So I'm Laura Waldrop. I'm very happy to be talking about the Carruthers Geocorona Observatory. We launched with IMAP, as Nathan Thomas just said, on September 24th. And we're really excited to be able to show you our first light images today in this presentation. Next slide. So we're the first NASA mission ever dedicated to studying what's known as Earth's exosphere. It's the outermost atmospheric layer. You can see the magnetosphere here, and it's truly huge. Okay, so it extends out multiple Earth radii, almost all the way to the lunar orbit. The reason we're doing this, we've known for a long time that the exosphere is the pathway for hydrogen escape. It's made almost exclusively of hydrogen atoms that used to be a water molecule on the surface of the Earth. And it dissociated, it became water vapor, broke up into its constituent oxygen and hydrogen atoms, and eventually floats off into space. At Earth, it's an exceptionally slow process. I know you guys are reporters and like the scary headlines, but there's no risk. We're not losing our water anytime soon. But this is the process by which Mars lost their surface water, and it's a ubiquitous process in space. Now that alone is a reason to study it, but you saw it in the movie's gonna loop. Well, it won't loop, but you saw it embedded within the magnetosphere. And because it's embedded in this plasma environment, what we've learned just in the last 10 to 15 years is that the interaction between the trapped plasma in Earth's magnetosphere and the neutral hydrogen in Earth's exosphere governs the rate of recovery from storms. In other words, that process by which they interact is the way that the Earth's magnetosphere loses the excess energy that these storms dump into the Earth system. And so knowing how many hydrogen atoms are up there, how they're distributed, how they change over time, will absolutely help us better predict storm recovery timescales. And so that's our second mission goal. Now, it is huge, and so it's very difficult to measure. Right now, we don't even have a model of how the exosphere works. It's not in any of our storm prediction capabilities, because in order to sense it, in order to measure it, you have to be really far away. And this is where we are building on the legacy of our namesake, George Carruthers. He built the first camera that's able to take a wide field image of the light that the exosphere gives off when the sun shines on it. It's a really special color of ultraviolet light. We call it Lyman alpha emission. And he put his camera on the surface of the moon. And when you're looking at the Earth's exosphere from lunar orbit, it filled up his field of view. It was much bigger than he was expecting it to be. The first time we saw how huge it is, that his camera went out to about 12 Earth radii. So each Earth radius is about 6,300 kilometers. Well, what we knew we needed to get farther away. So we're a mission of opportunity. The opportunity we took advantage of was the launch that would put us at the ideal vantage in halo orbit around this L1 Lagrange point. And so just like George Carruthers' camera, we have a wide field camera. You can see our field of view in red here. We also launched with a narrow field camera, nested, same bore site, also looking back at Earth continuously on this orbit. And what we're able to do then is look at that view close up to Earth, as well as a view of the global exosphere. And we're taking movies. Every 30 minutes, we get another image, and we're able to just watch how the Earth responds to these solar storms, how even just seasonal variations, and most importantly, how big is it truly? Because it's going to be a discovery. We don't yet know. So like I said, I'm really happy to show you our first slide images. Next slide, please. So these are everything that's not Lyman alpha. Okay, so we have multiple optical filters that we're allowed, that we use to look at the Earth. What you're seeing here is the Earth. The moon is in our field of view. Now, lunar orbit would extend way off. We're looking at it edge on. Okay, so the lunar orbit would go out beyond this, the field of view of this particular camera. We're seeing a little bit, you can kind of see it over here, of a crescent of the night side. So the sun's off to the right, north is up to the top. And what happens when we use our Lyman alpha filter for our camera? That's the next slide. There it is. It's huge. We get light all the way to the edge of our field of view. Now, this was our first slide image. We acquired it on that cruise phase out to our orbit about a month ago. So once we get out to the orbit, we'll be far enough away. But we're really excited that not only, we don't have any color bars yet because we're still calibrating the camera. But what I can tell you is this is at least 100 billion photons a second per unit area of our detector. It's exceptionally bright, plenty of signal. This is only a 5-minute image, so you can't even really tell that it's fuzzy, but our 30-minute images are going to be even crisper than this. So we're just really excited to make these discoveries. Thanks so much. And so with that, I'll turn it over to Rob.
Thank you, Laura. I'll also time up here. So I'm Rob Lillis. I'm the ESCAPADE. Let's go to the next slide. So what is ESCAPADE? ESCAPADE is a twin spacecraft, low-cost mission to understand the ways in which the solar wind interacts with the Martian magnetosphere and how that helps to drive atmospheric escape from Mars. So our two spacecraft are going to be orbiting the planet and sampling the plasma environment in situ. So we're going to measure magnetic field, we're going to measure the flux of ions, we're going to measure the connectedness of the magnetic fields using an electron instrument, and we also got a camera as well to take pictures, hopefully, of the aurora on the side of Mars. We are doing this for about 1/10 of the typical price of a Mars mission. So this is a really radical experiment by NASA in embracing higher risk tolerance in exchange for far more science per dollar. And I guess let's go to the next slide. We're getting there in a very unusual way. So this allows us to not just measure the way in which space weather affects Mars, which is going to be important when NASA wants to send humans to Mars. We're also going to be making measurements both at Earth and along the way to Mars. This is the at Earth part of it. And this was necessary because, as you may know, typical Mars launch windows open up only once every 26 months. But we launched about halfway in between two of them. So we spent about a year doing this kidney bean shaped dance around the Earth. This is the orbit of the Moon. This is the L2 Lagrange point. L1, which Larissa have been talking about, is over here. So we have all these trajectory correction maneuvers to sort of finely tune the path that we're going to take. And then at the end of that path, next November, we are going to head off to Mars. And we're going to be measuring space weather in Earth environment. In particular, we're going to be doing some discovery science because we're going to pass through the Earth's very distant magnetotail. So the magnetic field of the Earth's magnetosphere gets swept out behind it by the solar wind. No one's ever measured the tail this far away. So we're going to see how it responds to conditions upstream. Do we see magnetic reconnection there? What are the dimensions of the tail, et cetera? So that'll be exciting. And then, next slide. So starting next November and taking another 10 months will be our cruise to Mars. And this is a fairly typical, what's called a home and transfer to Mars. So we're going to be able to take two spacecraft measurements. The spacecraft are going to be, well, it's going to change in terms of their the distance between the two spacecraft, but like on the order of 500,000 to 1 million kilometer separation between the two spacecraft as we leave Earth here and we arrive at Mars in September 2027. And that's when our Mars mission begins. And so next slide. We're going to be characterizing the response of the Martian magnetosphere to space weather in two different ways. One, we're going to have what's called Campaign A, which is where the two spacecraft are like a pair of pearls on a string. They're going to follow each other, and they're actually going to cross over each other too, so that their temporal distance is between 2 minutes up to 30 minutes. We've never been able to understand how the system varies on timescales of less than 4 or 5 hours before. We've only ever had single orbiters. And when you see something change in your data with a single orbiter, you don't know whether you're witnessing a global change or whether you just entered a new region where conditions are different. With two spacecraft, you can distinguish those two things. And then next slide. So after about 6 months, we're going to raise one orbit and lower the other. So now they have different periods and they will precess. So Mars's bumpy gravity field essentially forks the orbits and they move, but they'll now move differently. Next slide. And so they will now get further and further apart. This will allow simultaneous measurements of much more distant regions of the Martian magnetosphere and allow us to see the real-time response of the Martian system to changes upstream. Before, we could either be upstream with the cause or downstream with the effect. Now we can see the cause and the effect simultaneously because it only takes about a minute, 2 minutes for a space weather disturbance to propagate through the Martian system. Before we had to wait hours and, things could have changed a lot. So this will be, we think, a revolutionary way to understand the Martian system. And, this is where understanding of the Earth's magnetosphere was, stuck in the mid-80s before we got multiple spacecraft missions. We're finally bringing that understanding and hopefully the revolution in, a leap in understanding to Mars. And that's it. So I will hand it to, I guess, our moderators.
Wonderful. Thanks for those presentations. Yes, we're going to Q&A now. So as a reminder, if you're in the room, wave at us and please tell us your name and what publication you're writing for when you ask your question. Folks online, please drop those questions into the Q&A box and over to Abby and her team.
Yes, thank you so much, everyone. That was great. Are there any questions in the room for any of our PIs or ourselves? Yes.
Hi, I'm Alex Woodsey, reporter with Nature. I have a question about Carruthers.
Sure.
So those first light images you showed, I'm just trying to imagine, like, the future images, are they gonna look a lot like that, just taken in different directions, or do you see like, are you gonna see like a lot of variation in the types of images you're getting, or?
That's a great question. They will look a lot like that. We will be looking at them from different angles, looking at the back of the Earth as the orbit evolves. And one thing I didn't mention, so even if the images look more or less the same, we do expect it to change in size as it responds to the solar environment and storms and so on. We also expect to see near Earth more significant changes. I didn't have a chance to go into this, but when a storm actually penetrates all the way down and you have, let's say, a big auroral event, the exosphere near the surface of the planet will change dramatically, up to 50% depletions near the surface, for example, as perturbations propagate around. But the most important, even if it doesn't change that much, the idea that we're getting multiple orientations, we'll be doing an algorithm similar to the way brain imaging works with MRIs. We call it exospheric tomography, where by looking at the same volume from multiple angles, you can build up that 3D picture then and watch it evolve over time. Sure.
Great. Are there any other questions? Yeah.
Yes, I mean, I'd actually like to follow up on that one. It's sort of the BBC. So I'm quite curious. So first of all, when solar winds and stuff come, is it sort of transparent to the solar winds and and so on? And are you looking for, as it were, density changes, temperature changes, maybe magnetic, responses to, again, you're saying that this is a shock absorber effectively for the auroral belts and so on. I think this
sort of. So they are neutral. So that we're looking at neutrals, and because they're neutral, they don't individually experience any magnetic or electric effects. And meanwhile, it's incredibly tenuous. So the density is very low. So as the solar wind's coming in,
is it sort of 1 per centimeter, cubic centimeter, 1 per
around 10 or 30. So around the dayside edge of the magnetopause, it's around 20 to 30 atoms per centimeter cubed. Yeah, it's very low. And so essentially it's transparent. But what happens where it's denser near the Earth's surface, and especially near the ring currents, there is an interaction between the neutrals and the ions, which effectively energizes the neutrals and cools the ions. So the energetic neutrals fly off, you've enhanced gravitational escape, but you've also slowed down the ring current. And it's that interaction that happens much closer to the planet, where the exosphere has the density to support essentially significant impact.
And so that's what you'll be really looking at.
That is what we're really looking at. That's exactly right. And to the extent that that process requires knowledge of the density and its time variability and its global distribution, that's the measurement that we'll be providing that frankly has never been measured before.
I have a question. My name is Molly Bentley. I work with Big Picture Science. You may have addressed this in the very first couple minutes, and I came in a little late. But if you were to synthesize, put together what we're going to learn about the heliosphere from PUNCH and also from IMAP, will there be discoveries if you could bring those data sets together? And that, for example, there was an earlier session yesterday where they were using AI to compile all this remote sensing data, and that was revealing new patterns. Is there a way of bringing together those two data sets that might reveal something new, or how do you combine them?
Craig, why don't you go first and then we'll comment?
Okay. Yes, of course, there will be joint science between us. There are two ways in which we can collaborate and plan to. The first is IMAP is always in the punch field of view. And so all of
It's always in the what?
It's always inside the punch field of view.
Oh, punch field. Yeah.
So we will be watching features that sweep over the in situ instruments that are on it now. But also we're seeing the sim heliosphere. And so we look through the inner heliosphere to the outer heliosphere on the other side of the sun. IMAP sees that all the time. So there's a lot of joint science that we can do, tracing effects through both the inner and outer heliosphere to the heliopause.
Yeah, and I guess I just add that you know, when you propose a NASA mission, you have to tell NASA why they should spend money on this thing. And so you have to give fairly specific things that you're going to do, and you can prove that you can make these measurements and those measurements. But the most exciting part is actually the stuff that you can't write down because you don't know it yet. And it's the true discovery science. And every time you launch one of these great missions, you get this true discovery science. There are a lot of opportunities for doing that in the individual missions, but there's also a lot of opportunity in doing that in the overlap between the missions. And AI is a new path, you know, that nobody's really tried for trying to put those together. And it may also be productive to try to use that to help put these data together. So I personally, people ask me what I'm most excited about at IMAP, and I always tell them I don't know, because it's the part that I didn't propose to do. That's the really exciting discovery science.
And even the AI out of it, and I didn't mean to bring in AI, it was just an example from yesterday. You know, do you know what you don't know about the sun, that you're hoping that when we bring these data sets, you'll say, okay, this is a whole revelation to us, because we're understanding the heliosphere from a couple of
We
different.
know a little about what we don't know, but we also don't know a lot about what we don't.
What's one thing that you hope to, just one thing that you don't know that is just a mystery, if I had to explain that to the public?
I would like to understand the heliosphere as a complete system. And I think that with these two missions, we have a good shot at doing that. At the very least, we'll get much better at that understanding. Up until recently, the fields of heliospheric physics and solar physics have been really distinct fields. From the discovery of the solar wind in the 1960s, we've studied the solar wind by sampling it. And I like to say that's like if you're studying human anatomy, but the only tool you have is an electron microscope. Likewise, we've been studying the sun with remote sensing. And that's like the tools of studying anatomy, right? We can see the big structures. For the first time, we now have Parker Solar Probe flying through the corona, getting a detailed view. And we have missions like Punch or IMAP that are studying the solar wind and its effects on the broad scale, the large and medium scales that are so important to see how things are connected.
Yeah, and then to go even further, the other part of IMAP, which is the imaging of the boundaries of the heliosphere and the interstellar medium and the interaction with the interstellar medium, again, we go back to remote sensing now, that we're able to sit at L1 and look out, and through these energetic neutral atoms and through samples of dust and neutral atoms, we're able to understand the scale of our heliosphere that's hundreds of AU away. So it's sort of remote sensing, in situ, remote sensing.
We have a couple questions online. Rick Levitt, who's a freelancer, asked, what is the reason for the halo orbit for Carruthers? And what is the reason for the dark border between the inner image close to the sun and the outer wide field image? And that is, why are the bandwidths no data overlap of the two instruments? If I got your question correctly.
So this is a question for me, yeah.
Okay.
Sure. So the halo orbit, it's actually a very large halo orbit around L1. And the reason is so that we're able to see the exosphere from multiple angles. So just like with a brain MRI, you have the camera essentially move its position around the brain, let's say, you know, the target that you want to do 3D imaging on. So it's a form of computational imaging. We're going to do the same thing with our Earth's exosphere, but that means that we need to have a large enough orbit that we're able to see it from those multiple angles to build up that, we call it viewing geometry diversity. So that's the orbit. And then as far as the images in that black border, the black border was there in all of the 4 images that I showed. It's just that there was no other light in the filter that blocks Lyman alpha. There is no other light anywhere in our solar system except for Lyman alpha light. And Earth's exosphere gives it off. Everywhere there's a hydrogen atom, the sun shines on it and it glows in this ultraviolet. And so that's what we're imaging with our Lyman alpha filter. Now, the reason we acquire images that block Lyman alpha is that we want to make absolutely sure that every photon we're measuring with our Lyman alpha filter truly was a Lyman alpha photon. And the Earth does emit, both the Earth and the moon, when the sun shines on them, it's like shining a flashlight on ice, right? It backscatters, essentially. It's a form of albedo. And then meanwhile, the Earth also emits, you know, oxygen emits in the ultraviolet, nitrogen emits in the ultraviolet. And so that with the first set of images, that was everything that's not Lyman alpha, we just want to make sure we know where it is so that we can subtract that from the Lyman alpha image and make sure we're isolating the Lyman alpha everywhere in that scene. I hope that helps.
And he has one more question, and then we'll get back to the room. The orbital track of ESCAPADE shows a green line that nearly goes to Mars and then dives back in. What's that? Are both orbiters going to Mars?
Green line that dives back in.
Maybe we have to pop back to that.
Only one got hooked on Mars and the other one got deviated.
I need to look at that again, sorry.
Okay.
Just go back.
Liza, can you repeat that question? I had trouble hearing that.
Yeah, so he asked, the orbital track of ESCAPADE shows a green line that nearly goes to Mars and then dives back in. What is it? And if are both orbiters going to Mars?
Yeah, both orbiters are definitely going to Mars. I think you could just go back a couple of slides.
Yeah, give me a second to get it back up for the online audience.
Oh.
That one?
No,
I think it's probably,
it's this one.
This one.
oh, well, the green line is the orbit of the Earth.
Okay.
I think
Or
it was in the animation.
did you mean the videos?
Probably the video, I think there was.
I remember.
Right, so the turquoise is the two ESCAPADE spacecraft. Red is Mars, blue is Earth. They will catch up there. So that's the end. I'm not sure what.
Probably thought that the green line was the top two lines were the ESCAPADE spacecraft.
Oh,
So do you mind saying it one more?
oh, sorry, gotcha,
Which
yes.
lines are which?
The two ESCAPADE spacecraft are represented by the turquoise dot. They're very close to each other on this kind of scale, which is the entire solar system. So, yeah, blue is Earth and red is Mars. Turquoise is both ESCAPADE spacecraft. Yes, they are both definitely going to be captured by Mars's gravity.
And Mars is red.
Yeah. Yes.
And if you could repeat for him the blue line.
Blue line is the Earth's
There
orbit
it is. Thank you.
around the sun, yeah.
Other questions in the room?
I do have another question, which was, and you did bring it up, Parker Probe. What's the future for Parker Probe? Because it did its famous perihelion last year. I don't know what the future, how long an extended mission.
So Parker right now is in orbiting the sun, and every time we have a perihelion and an apohelion, so we are never going to get to the closest point back. If you want to go, just because we're talking about it's like 30. We had the closest approach to the sun, but after that now Parker is orbiting the sun and gathering data, and we're still, the team is
For how many years?
We get back as close to the sun 4 times a year.
Yeah.
We get back in below
Oops.
10 solar radius.
And for how many years? I'm just interested how long it will go on working with your missions.
Are you talking about money or are you talking about?
On money? Well, maybe, well, maybe.
In terms of the orbit, practically forever.
Yeah,
yes.
but in terms of the
Spacecraft, a long time.
electronics and so on, how long it'll last, and the money.
Well, my
really.
little IBEX mission is still in its 17th year. It was a small explorer. The Voyagers are still going. Who knows how long Parker could go technically?
There's no plans to turn it off.
Not right now, no.
Okay,
It's,
that's what I want to know.
we're getting amazing data and science from the team and the mission. We don't have any plans.
Okay, thanks.
Any other questions in the room?
Just have another one. Do you think that if you could refine the warning system for space weather with these, obviously understanding the heliosphere better? I don't think you'd have something like the equivalent of the California shake alert, you know, where Californians, that's where I live, you get a couple minutes in some parts of Southern California at least, and then you can, you know, take cover. Maybe we wouldn't, you know, the Americans or anybody in the world wouldn't need a alert system like that for if there's going to be some kind of magnetic storm. But certainly scientists and the people who run the satellites would.
I'm so glad you asked that.
So it's a long rambling question, but the question is, could you actually have a more refined alert system so you'd actually have some time to respond?
So there is already an alert system going with current things like the Advanced Composition Explorer that sends data back all the time. But with IMAP, we have a much more complete set of measurements a much better set of measurements, things that ACE and the other missions haven't been able to provide. Those get sent down in real time and they'll go into models, NOAA models and NASA models. NASA's trying to develop more advanced models that hopefully someday go over and are used by NOAA as part of their warning system. And so those exist already and they're getting better over time, but with IMAP and the real-time solar wind we're sending that, there's an opportunity to sort of take a major step up in the quality of those. And I do think that there will be warnings for the people who need them. You know, if your GPS goes out and your tractor's out there on its own plowing the field and it's going to go over to the neighbor's field, somebody needs to know. And so, yeah, I do believe that that kind of thing will be much better in the years to come.
I can probably take a stab at that too, that IMAP and ACE and the various other in situ probes at L1 gives about what, an hour's warning, is that right?
30 to 40 minutes is typical.
But all of currently the forecast for any time scale longer than that from NOAA is based on imaging inside what I showed as a black circle, right? Inside that narrow region. And so we see a coronal mass ejection because of the largest space weather events for an hour or two as it leaves the sun, and then extrapolate across a day or two to decide if and when it's going to be a problem. We're hoping with Punch, we can actually track those. And ultimately, we're very excited about that. You can imagine, there's not much gray hair in the room, but before there were weather satellites, we tried to predict hurricanes from point measurements on the ground. And that's very hard at sea. But once we had geosynchronous spacecraft watching them, right, we could follow the tracks and see when and where they're going to make landfall. Similar kind of thing with instruments like Punch. We should be able to track these things across the solar system and actually have pinpoint accuracy data in advance. That's one of the ultimate goals of Punch. We're a science mission, so we are giving data to NASA or to NOAA as well as to NASA. And we hope that that'll improve their forecasting. But ultimately, that's where this research is going.
Have you been affected by the federal cuts to NASA, NOAA, and basic science? And is that going to affect any of these missions in the short term?
In the short term, we are fully funded for a prime mission. For anything else, assault.
Right now, we have received the president's budget, of course, and we are in a continuing resolution. But as you see, all these missions, they are either starting their prime phase or have already started it. And there is no impact to the science we're getting.
Good.
Other questions in the room? Oh, yes.
Helen Thompson, National Geographic. I was just curious, sort of along similar lines about the early warning systems here on Earth. I'm assuming that you guys are that NASA will use this data to sort of protect astronauts as they go to the moon. So could you speak at all to how it will refine sort of those reports as well and how they will get used in the missions?
Yeah, so that's another really important part. Saul mentioned that inside the Earth's magnetosphere, you have a lot of protection. So the space station has a lot of protection. You get outside the magnetosphere, you go to the moon, and you're sort of out there on your own. If you're in your spacesuit doing an EVA or something, you need to get back in. If you're on the lunar surface, you want to get, underground or habitat or something to save. So it'll be great if we get some notion that something may be coming from remote observations, but when you get the data 30 minutes ahead, you've got time to do something quick. And there are things that are already being built into the systems to take advantage of that. We may get even more advanced warning with IMAP. One of the really exciting things that we're looking at for the first time is energetic electrons, which tend to run out ahead of interplanetary shocks for several hours. And so we may get an in situ measurement, but several hours longer than this 30 to 40 minutes that tells us there's a big shock coming, and then when the shock arrives. And so I think we're going to end up with a set of warnings that come off of that. NOAA has a lot of that work, but when it comes back to protecting the astronauts, again, that's NASA.
I'd also say there's a similar, I guess, prototype early warning, at least the format for such a thing for astronauts going to Mars to have on like a tablet for their EVAs, which could be connected to a series of observations from, for example, IMAP or Punch that would feed into models that could be run extremely quickly that would then broadcast, either broadcast a warning to Mars or may actually be run at Mars so that the astronauts would have an in situ rapid, I guess, warning to say, hey, there's a storm coming. There's about 30 minutes before the SCPs hit. Go get underground. It's an extremely early stage effort. This is what is imagined. Asal can maybe speak to that some more.
So in spring, NASA and NOAA did an exercise together, the Artemis 2 space weather test bed, to exercise those roles and figure out how, as Dave said, NASA, we are in charge of our astronaut safety, but at the same time, NOAA is in charge of forecasting space weather. And they did that exercise together, and we keep working together to keep the astronauts safe.
I could just come back into go to the even bigger picture on this. All of this that you're talking about is sort of the short-term space weather that comes from the sun, which is most of space weather, but there's also a space climate aspect, which is long-term variations in the space environment. And the thing that's actually the dominant radiation source for astronauts going out to Mars doesn't come from the sun. It comes from outside in the interstellar medium. It's galactic cosmic radiation, galactic cosmic rays, or GCRs. That's part of what we study with IMAP. And the shielding that occurs in the outer heliosphere, regionally called the heliosheath, past the termination shock and inside the heliopause, actually takes about 90% of the typical galactic cosmic rays and deflects them away from the heliosphere. If it weren't for that shielding in the outer heliosphere, it basically wouldn't be possible to think about sending astronauts to Mars. And so we're studying this sort of longer term environment from remote observations on IMAP.
So there's a picture that is sort of, we're all painting here, right? Which is filling in. We are starting to see, we don't have it yet, but we're starting to see a systematic approach to space weather forecasting that's comparable to what we see on the ground, right? Where we have a broad variety of assets that are all working together. 3D imaging from Punch to track the storms, imaging of the heliosheath and of other effects from IMAP, in situ sensing of various kinds. These are all important and they feed into models, right? It's all part of what you might call a balanced breakfast for space weather forecasting that's comparable to what we do on the ground. For the first time, we're seeing that come together. It's good.
Awesome. And I think we have time for maybe just one more question. Any last ones? Nothing on? Okay.
Well, then, big thanks to our panelists today. You will be able to find these slides and the recordings in the press bulletin. We'll remind you where to find that. Abby, where can they find the first light images?
Yes, if you go to nasa.gov, we published just this morning first light from both IMAP and Carruthers. And if you can always also keep track with our blogs for each of these missions, where we post regular updates. And we also have a media availability later today for the IMAP mission, if you would like to speak to some of the co-investigators for some more questions on their first light images. So.
Great. So that IMAP thing is at 1 p.m. Central. If you're online, just request the link. In this room in 1 hour at 11 a.m. is the Arctic report card. And we thank you all for coming.
Thank you.
Thank you.
Let's see.